Hello, I'm Carla Moldaven, and today I'd like to talk to you about mathematical modeling. By this time in your course, you've probably already got a good foundation in linear equations, linear functions. You could graph an equation like y equals 3x plus 5 in less than 10 seconds. And if I told you some points on a line, you'd be able to find the equation for that line. But a lot of the work that you've done so far may be rather abstract, where the x's and y's haven't been put in a physical context. So today I'd like to look at that process of mathematical modeling so that the x and y variables take on a particular meaning in a context, and then we can interpret what the equations are saying in terms of that. When we talk about mathematical modeling, we're talking about creating a mathematical representation of some phenomenon, and we're going to take these observations and come up with a symbolic mathematical statement that describes it. And then if we need to, we can make modifications in that equation in order to get a more accurate reflection of what's really going on. And we can use our model to make predictions. The idea that we're going to model today is the concept of density. And density is a ratio of mass to volume. So for example, if I had a mineral that weighed 100 grams, and it occupied 50 milliliters of space, then simplifying that, I could say that the density of that material is 2 grams per milliliter. So we'll be measuring our density in the units of gram per milliliter, but we're dividing the mass by the volume to come up with the density. Density is also called specific gravity. It's just another name for it. And I've listed the specific gravity or density for several different minerals. You can find tables with a more exhaustive list, but this just gives you an idea of the density of some different minerals. You see that gold is very dense with a density of 19.3 grams per milliliter. Pyrite, or fool's gold, has a density of 5.0 grams per milliliter. And the one that we're going to focus on today is quartz, which in these reference materials is said to have a density of 2.6 grams per milliliter. So I have some specimens that I want to show you today. These are some that were collected at some of those places where you can go and pan for minerals in the mountains. And these are just some that I've collected in some times that I've been to some of those places, except for this one. This one I bought at Tellus Museum, and it's a quartz mineral that's in an egg shape. So it's a lot bigger than these others. And usually if I ask students, do they think these are all the same mineral, they'll tell me no, because look at all the colors that we've got. We've got purple and white and gold and a smoky kind of gray. And it turns out that the color's not really a good way of telling what a particular substance is as far as these minerals. But my geologist friend says that all of these are quartz samples. So what I want to do is to look at the density of each one of these. Say, do I really believe they're quartz based on the density? So what I'm going to do for each one of these is to weigh them on the scales to get the mass or the weight, and I'm going to get the volume by displacement of water. To show the displacement of water, I'll take the big one since it'll be easiest to look at. This one is a 1,000 milliliter or 1 liter graduated cylinder, and right now I have filled it up to 500 milliliters full, but you could have filled it up to any amount here. What's going to happen is I'm going to put the egg-shaped specimen down in the graduated cylinder, and the water is going to be displaced, and the amount of water that's displaced is the same as the volume of this sample. So I'm going to slide this down in here, trying to not make it splash too much. And then I'm going to take another reading, and I see that now it's up to 600 milliliters. So that difference going up from 500 to 600 milliliters is the volume of that. Now I can get the volume of the smaller ones by using the smaller graduated cylinders. So I might use this one to measure that smallest one. On one like this, I could probably use this 100 milliliter one. And right now I've got it so that it is up to 50 milliliters. So I'm going to see if that'll drop in there. May get stuck. Yeah, that one gets stuck. So let me do it in the larger one. Let me just go with another one. Let's see if that one's going to get stuck. Okay, right now this one is at 98. And if I drop that in there, it goes up to 108. So that one has a volume of 10 milliliters. Now to save time, I have gotten the volumes of all of these using the graduated cylinders and the displacement of the water. And I have also gotten the weight by using these scales. So in order to get the weight, I simply put the specimen on there, and it's going to read the number of grams. So this one is 12.6 grams of weight. I won't get my egg back out, but that one weighed 265 grams. So I've gathered the data for us for all of these specimens. Now what am I going to do with that data? All of them we said are quartz, even though they're different colors. And we found the mass using the scales. And we found the volume using the displacement of water in the different sized graduated cylinders. And these are the results. These are all of the ones that I measured and found both of those measurements for. What I did now was to take those and put them in the TI graphing calculator. And in entering your data in the calculator, go to the statistics button on the third row, third column, and choose edit there, hit enter. And I have already put in all of my mass and volume for each one of those mineral samples. In list 1, I have the volumes, and in list 2, I have the mass. And if I arrow down, I can see the results of each one of those. And I have not put in the large one yet. I'm going to add it in a few minutes. And the reason I'm not adding it in right now is because it's so much bigger that when I look at the graph, that point's going to be way off to itself. To look at the graph, go to second and y equals. And if your scatter plot is not on, go ahead and hit enter to turn it on. And you can choose the different kinds of graphs that you want. Right now we don't want a histogram, and we don't want our points connected. We don't want box and whiskers. We just want the scatter plot that it's already on. Our X values are going to come from list 1. Those are our volumes, and our Y values come from list 2. That was our weight or our mass. I'll keep the square box for the mark on these points because that's just easier to see. Now if I go to the zoom on the top middle row, I've got a zoom stat, which is number 9. And if I choose that, it's going to set the viewing rectangle so that I can see the numbers that I've got in my list. It's going to make it compatible with those. So if I hit enter, it's given me the points that I've got. I've actually already put an equation in there, so I'm going to go and deselect that equation so that I'm just looking at my points. These are the ones where the Y represents the mass or the weight, and the X represents the volume. And does it look like there's a linear relationship? Pretty close, doesn't it? And this is the difference between using real-world data and textbookish data, is that in real-world data, you're not going to have everything perfect. Why is some of this not perfectly on a straight line? Well, in the context of the minerals, you could have some impurities in one, or I can be making too fine of a distinction when I'm trying to get the volume, and I really can't tell if it's 0.3 of a milliliter or 0.4 of a milliliter. So these don't lie all exactly on the straight line, same straight line, but it does appear to be a linear relationship. So what I would do then is to go to Stat and over to Calculate, and I'm going to go down to Linear Regression and hit Enter. And I've already done this with those points in there. If I had data in other lists, I would need to tell it at this step what list to do the linear regression for. Since I've only got data in there for list 1 and list 2, I can simply hit enter and it gives it to me. Now looking at that, I think that maybe I've got a number in there wrong, and so that prompts me to go back and look at my data again. I have to go back and see if this looks reasonable. Let me check my data and see where my problem is. I've got the well, I tell you what, another thing I want to do, that should be 24.3 right there. Well, $15.6, $10.8, $4.3, $31.1, $7.3, 9.4, 12, 13.2, 16.1, and then there's one point that I left out. So I'm going to while I'm getting the line of best fit on these, I'm going to also go ahead and put in the large specimen that I didn't look at on the stat plot. So I'm entering 100 for the milliliters for that specimen, and then I'm entering 265 for the mass of that one. Now I'm going to go to statistics, calculate linear regression. And now I have my line of best fit for that data is y is equal to 2.647 times x plus 0.51, rounding those off. And what I have done is to go ahead and put that regression equation into my y equals. And what I'm going to do now is to look at, I'm going to turn that regression equation back on so that it gets graphed, and hit the graph button. And there's my actual data points with that line of best fit. Now, in this context, what does that line mean? What does the coefficient of x mean? The 2.647. That would represent the density of the quartz samples. This would be saying every time my volume goes up by 1 milliliter, the weight or mass is going to go up by 2.6 grams. What would the y-intercept, the 0.5086, represent in this case? Well, it represents that line of best fit would go through the 0.5 approximately. But theoretically, we know that if I had a sample that had 0 volume, it would also have 0 weight. So I would theoretically say that my y-intercept ought to be a 0. So notice that I've gone down into y2, and I have put in another equation, which can be a model for this situation. And on it, I'm letting the y-intercept be 0. I'm going to turn this one on also. And now I'm going to look at the graphs of those and notice how close those two lines actually run. So when I'm looking at the model there, it really didn't make a whole lot of difference which one I used. In a model, you're trying to come up with something that is as best a fit as you can get, that makes sense for your data, and you want to use it to make predictions. So let's go back and look at these results and think about again what did that line of best fit mean? We came up with the calculator doing the linear regression to get the line of best fit with y is equal to 2.647x plus 0.51. And we said that this 2.647 would have represented the slope of a line if you're looking at it abstractly, but it represents the change in y over the change in x, which in this case represents the change in the weight or mass compared to the change in the volume. So this would be saying every time my volume goes up by 1 milliliter, the weight is going to go up by approximately 2.6 grams. That's the meaning of the density. So we determined experimentally from these samples that I had that the density was 2.647 grams per milliliter. We decided that the y-intercept would be saying if the volume were 0, the weight would be 51 hundredths of a gram. And that's just the line of best fit for that data. It doesn't actually contain that point, we know, because if the weight were 0, the volume would be 0. So 0, 0 ought to be the theoretical y-intercept. So we changed it to y is equal to 2.647 as a model for this situation. So now I've got a predictor equation, a line of best fit for this data, and I could use it to answer some questions. I could have a question like, what would be the weight of a quartz sample that has a volume of 40 milliliters? So I would be looking for the weight, which is y, and that would be equal to 2.647 times the volume, which is 40 milliliters, and multiplying that out would give me 105 and 88 hundredths grams. If you think about your units, your density was 2.647 grams per milliliter. You're multiplying that by 40 milliliters, so your unit is going to be grams here. So multiplying the 2.647 times the 40 gave us 105.88, and we knew that we were coming up with grams for our units. Similarly, we could get the volume if we know the weight. So this time we know y. We know that it's 450 grams, and that should be equal to the density, 2.647, times the volume, which we're calling x. So to solve that simple one-step equation for x, we would divide 450 by 2.647, and that comes out to be right at 170 milliliters for the volume. Does that sound reasonable? If our egg had a mass of 265 grams and it was 100 milliliters, does that sound like the comparison to 450 grams and 170 milliliters would be the same ratio? And yes, it would be. So we've looked at the relationship in this experiment between the volume of a mineral sample and its mass, and we found out it is a linear relationship. And you know that any linear equation can be written in the form of y is equal to mx plus b, where m is the slope and b is the y-intercept. We could also say that the weight is directly proportional to the mass. If I have y is equal to mx, and we said that the y-intercept would be really 0 in the real situation here, because if you've got 0 volume, you've got 0 weight. So my equation then would take the form of y is equal to mx, and that's a special kind of linear relationship. That one is one that we call a direct proportion. So it's simply a linear relationship, but we have a y-intercept of 0. In our case, we have 2.647 as our coefficient of x, and we could also refer to that 2.647 as the constant of proportionality. We knew, based on literature from geology, that the density of quartz is supposed to be about 2.6. But if we had been the geologists coming up with those charts, we could have come up with that by doing an experiment like we did today. We will be looking at some other models in your study of mathematics. We'll look at some that are not linear. We'll look at others that are linear. I have some experiments that I hope you can do on your own. There are other things that we look at that the model just makes sense. I don't have to really gather any data or do any experiments. For example, if you were looking at a business application, you could say that to calculate your profit, you would take the amount of revenue you take in and subtract the cost that you've spent on the manufacturing of the items. So hopefully in this session on mathematical modeling, you're beginning to see that variables stand for things that you're interested in a relationship between, and that you're gathering the data and you're coming up with an equation that tells me mathematically how these two variables are related. And you will find that there are exponential functions, models for exponential, rational equations, logarithmic, logistic, all kinds of models. And this is where mathematics really becomes useful, being able to make predictions based on the mathematics that we find, the models for those. Thank you.